Okay, these are the notes for the extreme value theorem. This is in Unit 5 of AP Calculus. We've already done the mean value theorem before we did the intermediate value theorem, and so this is another theorem. This is where I feel students get, I guess, muddled because they're seeing all these theorems and they're not sure how to apply them and how to memorize them all. So the wording in this one helps a lot because you're looking for extreme values. Extreme values in calculus are called extrema. So if a function is continuous on a closed interval, which is how the mean value started out, so then the function has both a minimum and a maximum on the interval. And these three pictures that I'm showing you give you some minimums and maximum. There's different words for minimum. There's relative and there's local. Relative and local means compared to everything else around it. Then we have also absolute and global. Extrema. Absolute and global means they're definitely the maximum or the minimum. So a relative or a local extrema would be in my family. I'm relatively short. I don't think 5'8" is short for a woman, but I have got some uncles and some cousins, even female cousins, who are over 6 feet tall. So I'm relatively short. I'm a relative minimum. Absolute, so my tallest uncle is 6'6". He is the absolute maximum. So as far as mathematics goes, when you're looking at these equations or these functions that I have here, this point right here is going to be the absolute maximum. This point here is going to be the absolute minimum. And these are interior points. So if this were my function from the closed interval from A to B, this is the highest. It's the absolute or global max, absolute or global minimum. This graph here, if this were A and this were B, the absolute maximum is at A and the absolute minimum is at B. This one here, this is your absolute maximum. This is your absolute minimum. So if this were A and this were B, B is neither extrema. This is your highest point, this is your lowest point. So I have a couple more graphs to help explain what you're looking at. We're going to start using the term critical numbers. Critical numbers occur when the derivative equals 0 or when a function is not differentiable. Critical numbers are where, it's the x value, where the relative and global extrema will occur. So here's a couple examples of graph. There's a critical number at -3 because the slope is 0. It's a relative minimum. A tangent, if you draw a tangent line, that slope is 0. There's a critical number at -1 because at x equals -1, it's not differentiable. It's a point. There's a critical number at x equals 2. Once again, it's not differentiable there, so that's why it's critical. And there's a critical number at 4. And that's going to be a tangent line would equal 0. The next one, this is all differentiable. It's continuous. And there's maximum minimum values. So there's critical numbers at -2, at 1, at 2, and at 6. There's something else going on in here. See this little loop here? We'll talk about that later. But that's what critical numbers are. So here's a couple examples to work through this. So the way to find a critical number is that you either have to understand the function well enough to understand any points of discontinuity, or you can use algebra techniques. We're going to actually take the derivative of this and set the derivative equal to 0. So I have f prime of x equals 12x cubed minus 12x squared. I set that equal to 0 to look for the critical numbers. So I can factor out a 12x squared, and I get x minus 1. So I get x is equal to 0 and x is equal to 1. Those are my critical numbers. And if I were to look at the graph for a second, and I'm not going to put a y scale on this, I have graphed this already, and the graph looks like this. So this is the point -1,7. This is the point 216. So now I want to check what's happening at 0 and 1. So I first check my left end. My left end point is the point -1,7, like I've said there. I'm going to check my critical number. So if I put a 0, and this is where I have to put it back into the original function. Don't put it back into your derivative, put it into your original function. So 0 goes into here and I get the point 0, 0. Then I check the critical number 1. 1 goes into the original function. So f of 1 is 3 minus 4 gives me -1. And then I check my right endpoint. And that's this point here. I get the point 216. So what happens is this point 216 is going to be my absolute maximum. This point here, 1, -1, is going to be my absolute minimum. Zero, 0 is here. So it's a relative minimum, and -1,7 is absolutely nothing. It's just an endpoint. Now if I did the open interval for the same function, if I looked at it from here to here, I would have a relative minimum right here at 1, -1. There are no relative maximums, and 0, 0 ends up being a point of inflection, which we will go over later on. Watch the live lesson for more examples. This concept typically is not difficult, but it can be a little bit tricky.